And now we are very pleased to have Professor Artan Sheshmani, who's a professor here at BIMSA. And his research area is algebraic geometry. He did his PhD at the University of Urbana-Champaign, and he held several positions afterwards in the USA, including MIT and Harvard. In fact, he spent 10 years at Harvard, and now he's a professor here at the Beijing Institute of Mathematical Sciences and Applications. And he will talk about today about D-geometric Hilbert and Quot DG-Schemes. Thank you very much.
Thank you. All right. Can you hear me? Yeah, okay. Thanks for the kind introduction, and I would like to thank the organizers for inviting me to this Congress. I'm not one of the organizers. Okay. So, yes, the title is here. I will talk about study of global and maybe virtual geometry of moduli space of solutions to nonlinear PDE. These have, under deformation theory, these have applications in enumerative problems, for instance, Donaldson-Thomas theory, Gromov-Witten theory, Pendragon-Thomas theory, mirror symmetry. All these nice moduli spaces are originally just moduli spaces of solutions to systems of differential equations that come handy maybe in mathematical physics, quantum field theory, supersymmetric field theories, etc. So this is based on joint work with Jacob Kritzka, who's sitting here, my postdoc here, who's finishing, going to Europe soon, and work with Professor Yao. But particularly, it's based on the last two papers on Hilbert and Quot schemes that we posted on arXiv last week, 1 week before the Congress. Okay, so the roadmap to my talk here is actually starting from analytic presentations. These are differential equations. We look at them and we make some geometric object, or maybe geometric spaces, a space of solutions to these differential equations. And this is the core to this presentation. So we are not interested in a given differential equation and its solution space. We are given in many, 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 infinitely many differential equations. We start with the differential equations like this. It's written in terms of independent variables, some functions and their partial derivatives, and we keep taking derivatives of both sides of this equation further and further. So we obtain new differential equations, and we obtain solutions to them. Then we add them all after infinitely many times of differentiations, and we would like to study the solution space that we get from this. The idea is that if you allow yourself, start from a differential equation, and this is called prolongation, by the way, prolong it infinitely many times, some global features emerge, and you can use the language of algebraic geometry to study those global features, and you can actually study geometry of these spaces that you encounter in between in each step also. So, well, we associate some algebraic structures to these spaces in each step. These are called symbolic structures. We study how algebraic geometry can understand geometric integrability conditions on PDEs. We even find some way of giving them some kind of a label or ID. Let's say we look at a family of these differential equations and all of their infinite prolongations, and we study some numerical polynomials similar to Hilbert polynomials for them. And once you have defined all of these things, you can just construct Quot and its Quot scheme for them. So you can obtain parameterizing spaces like Hilbert scheme, Quot schemes for these spaces. The idea is here is that how you want to incorporate this concept of starting from some solution space but prolong it infinitely many times. That's the idea. And then once you do that, for this each infinite chain, you want to have a family of infinite chains of these spaces and parameterize them. Okay, so this is basics of differential equations. You have n differential equations. You start from a vector valued function with m components. You can think of this as sections of a vector bundle of rank m. You have n independent variables. Then you look at expressions in terms of x and u's and partial derivatives of these u's. And these are differential equations you have. And the common intersection of the locus of all of these differential equations give you the solution space to this system. You can use the multi-index notation. In my talk, I'm here and there, I will use it. So if you take the alpha component, you take the derivative with respect to this kind of multi-index, this being sigma 1 plus sigma n, that means that I'm taking derivative of u with respect to x1 sigma 1 many times, with respect to xn sigma n many times. If sigma 1 to sigma n are less than k, that gives me a differential equation of order k. There is this simplifying assumption for the purpose of the talk today that all of these systems have differential order k, but we don't need it. In our paper, we didn't assume such thing. Once you do that, then you can actually ask yourself, where is this zk sit? So those of you familiar with algebraic geometry, well, when you set functions equal to 0, those give you ideals. So what's the algebra? The algebra is not just x and u. Those are given by algebraic structure of just E, but also given by its kth order differentials. So that's actually in the context of community in differential geometry that they know this. I mean, this is the kth jet space of E. It's the space of sections of E up to kth order partial derivatives. Algebraic geometers also understand these jet spaces. We have jet spaces associated to sheaves, vector bundles, everything. So these equations being set equal to 0 are ideals in subspaces of jet spaces, which are cut off by ideals of these functions. Once you have those ideals, you can look at the structure algebra of jet space of the bundle, quotient them, and you have the structure sheaf of these solution spaces, exactly like algebraic geometry. Now, because I'm going to use it, let me remind you of how the algebra, because I'm not a differential geometer, how the algebraic geometer thinks about these. So I have the vector bundle, a straight E, and I have the sheaf associated to it. So this is kind of sheaf of coefficients, right? So you see that in Hartshorne, so it's a dual thing. All right, so one way of defining this jet space of E, this is the vector topological bundle, but I want to define for you the structure sheaf of this topological bundle, which is the sheaf of jets on this sheaf E. So one way of doing it, algebraic geometry understand these things by looking at infinitesimal information of X, the underlying variety, via its diagonal embedding into its twofold product. So you can embed X inside here. Let's say this thing has an ideal like that. So simple things. So you have, well, okay, so let's be very, very pedantic as if you're doing basic algebraic geometry. So you have this, two projections like that. Then you can pull back structure sheaf of X. It's structure sheaf of X cross X. It's inside there. And then this is the ideal of diagonal sitting inside there. It's a subsheaf of this guy. Well, fundamental theorem of algebra tells you that this is basically just this modulo this. It's obvious, right? Okay, one other thing you can do is, well, this is also, by the way, the same as O of delta, right? O of the diagonal. So what you can do, you can fatten diagonal inside this twofold product. If you're, yeah. No, but I want to, no. It's not always first. Yeah, that's right. Yeah. That's true. I lower star of O of delta. Yeah, that's true. That's right. Okay, so one other thing you can do, you can actually fatten the diagonal. So you can fatten the diagonal and you can describe O of 2 delta, some kind of canonical short exact sequence for O of 2 delta. And this is O of X cross X modulo I delta square. Okay, so I can have this one also. Okay, I know that everyone knows this, but anyways, if there are students and so on. So then you can basically see that these two things are related to each other. So in fact, you can have this guy, which is O of 2 delta. You can have this guy, which is O of delta, or push forward of delta via the embedding. And then you can have I mod I square inside there. So this is also I of delta mod I delta square. what then you can do is you can basically push forward everything onto X. So you can push forward this, then this maps to O of X, and Artan tells us that you will get sheaf of Kähler differentials of X. So this is how you define sheaf of Kähler differentials, and this is basically the definition of first jet of O of X. Basically, this is the first jet sheaf. Now, so here, this is the jet 0 of O of X, which is just no jets on X. If you have a sheaf or vector bundle, instead of looking at the structure sheaf of X, you had a vector bundle, everything gets basically twisted version of this thing. You can have some sheaves, put some sheaf in here, like this, tensor E, for example. Oh, and this also gets twisted by that sheaf. Okay, and this short exact sequence is basically also a known thing. So this is nothing but Atiyah class of extensions of this, which is the abstraction to having some algebraic connection on this sheaf. Okay, so these we know, and then if you did this, you can take this operation, apply everything to jet 1 of E, get jet 2, jet 3, jet 4, and anyway. So you can have jet k minus 1 of E, and then here you will just get something like sim k of sheaf of Kähler differentials tensor E, something like that. And this is familiar object for community of PDE. This is called co-symbol. So this is this co-symbol, or the sheaf associated to co-symbol of E. Okay, so this is what this symbol are. Symbols or co-symbols are. Okay, I'm gonna get back to this co-symbols. So the idea is that this sheaf of K jets on E surjects onto, so now you have some topological space, vanishing locus inside space jet K of a straight E, and structure sheaf of this thing surjects onto the structure sheaf of that thing. This can be realized as a quotient of this sheaf over here. Okay, so that's the idea. All right, so I think I told you everything the way algebraic geometry understands these things. So once you have differential operators, look at differential equations over the K, you will get these cut solution spaces. You have a more general version of differential operator from one bundle to the other. Yeah. No. Yeah, no. Yeah. Total space, exactly. So you can have a notion of case order differential operator from E to F. And that's in one-to-one correspondence to OX linear sheaf homomorphisms from OX linear homomorphisms from jet K of E to F. So that's our just more sophisticated version, like differential operators taking values in F. So that was differential operators on E taking values in O, but now you have twisting these things with sections of F. Now you have this prolongation. As I said, you can take derivatives. If you have a differential operator of order K from E jet K of E to F, you can keep taking derivatives. If you take the derivatives L many times, any way you want, that gives you a homomorphism from, well, order of differentiation goes up from jet L plus K of E to jet L of F. That's what you will get. Okay, so good. And then the solution spaces to these more sophisticated differential operators are given by the kernels of these maps that you will get. So these are again solution spaces. You can do this prolongation taking derivative infinitely many times, and you will get union of all of those solution spaces, and that's what we call infinite prolongation of solution space. Okay, so that's what we want. In each level, you have ideals being kind of cutting out these zk plus l's or zk's inside the structure algebra of the topological L plus k jet space. Or you can think about sheaf theoretically or dually. You can think about jet sheaves of the dual sheaf. Okay. Iz infinity after infinite prolongations are differentially generated. So in coordinates, if you are someone from community of PDE, these are written in terms of partial derivatives with respect to the independent base variables and derivatives on the fiber. Okay, so this defines some kind of integrable distributions. And this is this total derivatives that we have. Okay, so this is the description. Now, as you can see algebraically or analytically, you can keep prolonging. So you will get some infinite tower of jet spaces. So first you have the variety, then you have the vector bundle, then you have, this is jet 0, jet 1, jet 2. You get some infinite towers. And the subscheme sits as a sublocus of each topological space. Okay. Now to these subschemes, you can do two types of operations. One is you start from a subscheme in here, project it down, or start from a subscheme in here and prolong it. So let's say I have jet k of E, I have subspace k here, and I have jet k plus 1 of E, and I have subspace zk plus 1 in here. So one thing I can do, I can include this in here and project down. Let's call this something I pi, and then if I do this, pi k plus 1 OI, this is, let's look at the image. So pi k plus 1 OI of zk plus 1. This thing sits inside here. It's not necessarily equal. The other thing I can do, I can take this thing, this is given by some ideal of some fk equal to 0. Then I can look at the functions, the system, and take its derivative, take the derivative, and compute some kind of fk plus 1 equal to 0, and ask myself what is the ideal, and then ask what is the 0 locus defined by that ideal. That's the prolongation. So if I look at the 0 locus of this ideal, this is the first order prolongation of zk. So first order prolongation of zk somehow is a subspace in here. So first order zk is a subspace in here, and actually this thing sits inside there. So in fact, when you project down and prolong up, these are not equal to each other. It's only true that they will become equal to each other if you assume what is called integrability, actually. So algebraic translation of integrability is that if you do projection and prolongation, you get these inclusions, this way and this way, these become equalities. If you have integrability, then in some sense it tells you that you can go up and down in this tower any way you want. And otherwise, you don't have compatibilities between the solution spaces. Okay, so that's what you will get. Now, this is an example. Here is the wave equation. Okay, so I have only one function. So my E vector bundle is a line bundle. Sections are U. I take its derivative with respect to time and spatial variables. So I have n plus 1 independent variables and one function, and also I have partial derivatives. Because I'm taking second order partial derivative, this locus sits inside jet 2, topological jet 2 of E. But I can actually take further and further differentials with the multi-index whose cardinality can go all the way to up to infinity, and then I can construct these z infinities out of it. So this is an example. Vinogradov, who is actually academic father of Jacob, has this he passed away, am I right? Yes. Had this philosophy that in order to understand global features of PDEs, you need to infinitely prolong them. Only then the global algebraic features emerge. So this idea actually is an old idea. You start from a differential equation, but prolong and study it algebraically. Okay? All right. Another reason for prolonging things is the following. When we go up and down in this tower, when I look at this, when I look at the equation that gives me this sublocus and then take the derivative and look at the sublocus again, there are many ways of getting a prolongation up there. You can take the partial derivative many ways. You can take with respect to one variable or the other. All of them sit inside one more ordered jet space. So in fact, you can actually see that if you just want to study these different solution spaces in each level, because you have many ways of getting to that level, it's hard. They have nothing to talk about with each other because you get there different ways. The geometry is different. But if you allow yourself to prolong infinitely many times, eventually you will have some stabilization that happens. Something like Hilbert basis theorem. So these ideals of differentials actually stabilize with respect to the total derivation, hopefully. And then you can study them all together, right? So allow yourself to infinitely derive so that your ideal becomes stable under the action of total derivations, and then study everything. Once you do that, you will get naturally short exact sequence of infinite prolongation ideal, O of the jet infinity bundle, and a structure sheaf of the infinite prolongation solution space. Then that naturally gives you some interplay between regular algebraic geometry and D geometry. In regular algebraic geometry, you have polynomials. Here you have differential equations. Regular algebraic geometry, you have commutative algebras over some field. Here you have commutative algebras over a ring of differential operators. Here you have free modules. There you have free modules over the structure algebra of jet infinity bundle. Here you have solution space, same as that. Affine spaces, d-affine spaces. You have the structure sheaf of affine loci and the structure sheaf of affine loci or d-affine loci. Okay. So, question, is there a moduli space of D subschemes? So when I say D subschemes, it means always for me that I have infinitely prolonged it. That's what it means. Okay. Okay. You took the picture? Yes, great. Yeah. Yeah. Yes. What do you mean solution? Yeah. In each level, there is a solution space. Can we identify it? Kind of no. It's very difficult to exactly know what these are singular, by the way. They can be singular, everything. We are not doing like what PDE people do, assuming that all the solution spaces are always a smooth manifolds. We don't have such assumptions. We are doing things algebraically. All right. So let me tell you about this parameterization. So Hilbert schemes and Quot schemes algebraic geometry do the parameterizations, and I need to tell you about a little bit of this ingredients, how to modify these things for D geometry, and define for you D Quot and D Hilbert functors. Okay. So Hilbert and Quot schemes are algebraic geometry. Here we are assuming that all the schemes are locally Noetherian over some algebraically closed field K. So for those of you maybe students in the audience, I see some students. You have a variety. Let's assume that this is projective, but you want to do things over families. So you have a variety over some scheme S, and which is projective. So relative, you have some relative ample line bundle. That means every fiber of this variety over every geometric point of S is a projective variety with ample line bundle. You would like to parameterize subschemes of every fiber of this family such that they all have some kind of common ID. Maybe this ID could be a polynomial. So Hilbert polynomial comes in handy. So Hilbert functor is a functor from opposite categories of schemes over S to sets. So this opposite category of the schemes are things like T. As soon as you take this operator, categorical operator, which is a functor, apply it to some T, well, X is over S and T is supposed to be over S, so you can define this fiber product. And this functor is kind of spits out for you elements of some set. What are those elements? They are subschemes of this guy, such that, well, you can take a fiber of this guy over a point in here, over a point of T. That should give you some subvariety of X. And you want the Hilbert polynomial of a structure sheaf of that subvariety to be equal to P. So now, using polynomials, I can parameterize subschemes. So that's the idea. So if you want to parameterize subschemes, you need to look at functions defined on those subschemes. This is absolutely very important. So if you have something like this, then that means you're looking at quotients like this, well, ideal of y in x, right? Such that Hilbert polynomial of this guy, you want it to be fixed. Well, Grothendieck actually tells us that you can do a more general construction. So you can actually look at not just these kind of quotients, take any coherent sheaf and construct quotients of these coherent sheaves, which are defined over this space, whose fiber over every point of T is an actual coherent quotient sheaf on X, such that, like this, such that Hilbert polynomial of this sheaf is equal to P fixed. Of course, if you can construct a space like this, once you put this equal to O, that's the same as parameterizing ideal sheaves and the Hilbert scheme. So Quot scheme specializes to Hilbert scheme. Okay, so this is Grothendieck's construction. All right, so fixing this Hilbert polynomial is absolutely very important. Well, there is this statement which is called regularity statement. So what is regularity statement? If you have a coherent sheaf in the abelian category of coherent sheaves on a variety, then there is something called Castelnuovo-Mumford regularity condition. So it would be called Castelnuovo-Mumford M regular if after twisting this coherent sheaf with a large enough integer, remember the variety is now projective, so I have a line bundle on it, so I can take O of 1 to the tensor M. So this makes sense. The Serre twist makes sense. So there is some large enough integer such that after twisting my sheaf large enough, the twisted sheaf doesn't have any higher cohomologies. This is absolutely very important because it actually tells you a lot about boundedness of these families and also kind of structure of the Quot scheme that Grothendieck constructs for you. Grothendieck has a statement says, well, if you have a family of quotient sheaves, okay, and you fix not maybe one polynomial, even finitely many polynomials. It could be not necessarily one, finitely many. So finitely many possible polynomials for these G's. Okay, if you have such thing, then this family will be bounded. Family of coherent sheaves will be bounded. Not only that, all members of this family satisfy the property that there will be some integer for them, after twisting which these members all become vector bundles, meaning all higher cohomologies of these things actually vanish. In fact, if you pick the largest integer for all members of the family, there is an upper uniform bound for the Castelnuovo-Mumford regularity. Okay, why is this actually telling you something about Quot scheme structure is actually as follows. Let's say you have a bounded family of these things, this quotient sheaf G, and their Hilbert polynomial is P. Together with this Castelnuovo-Mumford regularity, you can twist this thing high enough, and it becomes a vector bundle. Once it becomes a vector bundle, you can realize it as quotients of some vector bundle. It's literally basically a space of sections of this kind. It's the only thing that remains there. So basically V tensor O, like that, O of X, let's say. And this dimension of V is dimension of space of sections of G twisted by M. And there's nothing else. There's no higher cohomologies actually. So it's after twisting high enough, this thing becomes a vector bundle quotient of a vector bundle with a vector bundle kernel. And the space that parameterizes vector bundle quotients of a vector bundle is the Grassmannian. So it actually tells you after twisting high enough, the Quot scheme embeds into a Grassmannian. But then Grassmannian embeds via Pulucker embedding into a projective space. So in fact, the interplay combination of Castelnuovo-Mumford regularity and boundedness of families allow you to see that the space that represents Grothendieck's Quot functor is a projective scheme. And this is very important. So it has some ample polarization. So we want to do this same thing. We want to look at differential equations, modules theoretically, and all of their infinite prolongations and construct some kind of regularity condition for them, some notion of Hilbert polynomial for them, and obtain same thing. So we want to prove boundedness, and we want to relate it to regularity condition and get some similar statement, similar construction. Okay? So, by the way, there is a different notion of regularity also in algebraic geometry. Let's say V is some n-dimensional k-vector space. This is the definition of Kojoule complex for V. You can dualize it, and that's the dual is the polynomial Derham complex. Okay? And of course, I mean, Derham complex and the Kojoule complex are dual of each other. All right. Now, if you have some module over a polynomial ring, which is given by the tensor algebra of V, this vector space, you can also define Kojoule complex for these modules. Obviously, we define Kojoule complexes for sheaves, bundles, everything. And if your module is graded, the Kojoule complex will be having some intrinsic extra grading, with respect to which you can define some kind of bi-graded cohomology of the Kojoule complex of that graded module. So it's actually, okay, so I'm not going to spend so much time. So this is the grading on the module, and these are the gradings on the Durham. So then you can define HPQ from this bi-graded complex, and that actually defines for you a notion of an equivalent notion of regularity. So a module which is graded is regular if infimum of, if you can basically, regularity is given by infimum over R of OPQs where HPQ vanishes after some degree. So that's basically the regularity of the module. You can basically do this for what I just mentioned over there, and you see that these are equivalent. Okay, this is the one that we want to use. Why do we want to use? Because this extra grading for us is going to be some grading induced by prolongation. Remember that I start from some module given by ideal sheaf or a structure sheaf of some solution space. Okay, I can construct it Kojoule complex, no problem. But I don't want to do that. I want to infinitely prolong it, so I have this extra grading. So I want to take all of these graded pieces and add them up, get the graded module, and then define HPQ homology, and basically then regularity from that. That's the core, why we want to use this. Okay, so all right, so this is this is some kind of break in the middle, let's just say. So after, let's say, you construct these spaces, Quot scheme, Hilbert scheme, these are often ill-behaved. They are highly obstructed, they're singular. In some places they are singular, smooth, but often singular. So Kontsevich many years ago actually suggested that often all of these parameterizing spaces or moduli spaces have some kind of hidden smoothness. Well, you need to kind of embed these things in what is called derived extensions or derived enhancement of these moduli spaces. That has to do with extending algebraic geometry to homotopical algebraic geometry over chain complexes and things like that, or notions of the schema stacks to drive the schema stacks. We have done this in our paper, but I don't want to talk about it. I'm just telling you that we have done it so that if you are interested, look at our papers. As long as it concerns this construction of Quot schemes and Hilbert schemes, the derived schemes and stacks were defined by Towen over simplicial categories, and also by Chukan, Fontanin, and Kapranov over differentially graded algebras. And we also worked on those with Borisov and Katsarkov, and we actually showed that these two constructions of Towen and Fontanin Kapranov are the same. Now, separately somehow speaking, we were discussing kind of studying Quot scheme of perfect complexes on Calabi-Yau-4 varieties. Quot scheme of complexes on Calabi-Yau-4 varieties. And for a different purpose, this was in joint work with Professor Yao and Borisov and Katsarkov. And Misha Kapranov was very kind to, he sent us an email and he said, there is an error in our construction. So their construction of R-Quot and R-Hilb has this problem that the derived schemes are not represented by finite type DG manifolds. So they are not finite type. So that basically collapsed our constructions, and for practical uses, actually purposes, these cannot be used anymore. So we were so grateful that they told us so. I'm just announcing in here, so this thing actually got published this year, and we actually fixed the error, and we proved that these derived Quot schemes are representable by finite type DG manifold. Of course, we are grateful that Misha told us about the error, and later actually he reviewed our constructions also, so he gave many comments. All right, so going back to algebraic D geometry, we have some kind of infinite grading, remember, but we are not doing derived things. Our x is fixed. Our E is given, but we are doing this infinite grading in terms of partial derivatives of sections of E. That's one way of going to infinite chains. If I allowed algebra of X to also be extended to some kind of DG algebra, that would be the derived Quot stack. So we are not doing that yet. Okay, we are just keeping X as it is. Base polynomial algebra of X is still at this, but we want to prolong only. Okay, so these I talked about. All right. So we want the Quot functor to parameterize ideal sheaves or structure sheaves of solution spaces after infinite prolongations, but up to isomorphism. That means commutativity of obvious diagrams like this. We want to have this assumption that infinitely prolonged ideal sheets are always remaining proper. We want them to be actual subsheets. We don't want it to become the whole space. It's important. The other thing is we want to make sure that after infinite prolongation, solution space is non-empty. Let's say I give you something like a differential equation, and I take derivatives. I can maybe find some way of taking derivatives that after taking the derivative, everything cancels out. So I get 0 equal to 0. We don't want that. We want this to always give us non-empty solution space. Okay, so we don't want the ideal to collapse. All right. Yes, we want to assume integrability. That's right. That's right. Okay. Now the question is this a space, the Quot space, the Quot of ideal which is representable? I have defined a functor, and is it representable? And whether there is a derived enhancements, okay, I'm not going to talk about it. Okay. In order to define this representability, I need to define this notion of regularity condition, something like Casanova-Mumford regularity. For the nonlinear PDEs, we need to look at geometric symbols. Okay, so this was the symbol of E. If I restrict these guys to the solution spaces, like that, this I'm going to call n of k, and this is, I'm going to call it co-symbol associated to zk. So you have a co-symbol of the ambient jet bundle, and you have a co-symbol of the solution space sitting inside that ambient jet bundle. All right, in order to define this regularity condition, you need to look at these co-symbols. All right, first of all, let me tell you that this symbolic formalism is way more concrete and kind of rudimentary than the theory of PDEs. In fact, using abstract algebra, you can define all of these notions. So if you have two vector spaces, look at symmetric algebra of V dual times W. You can look at some subvector space just abstractly, has nothing to do with PDEs, let's just say. And then you can actually abstractly define the notion of prolongation. So prolongation is all things that you see. This sim k, they sit inside sim k plus 1 V dual times W. And the way you get these things, you want Derham differential, you construct the Derham polynomial complex for them, and you want the image of the Derham differential to sit inside nk VW. If this is the case, this subvector space is called the symbol. All right, so this is very abstract. This I don't know anything about differentiation. This is just morphisms, nothing else. All right, so this tells you that given V dual and W and symmetric K algebra of V, you can get a whole sequence of symbols. You can get vector spaces that are satisfying this property, and that gives you a sequence, prolongation. This is algebraic notion of prolongation without knowing anything about analytic differentiation. Once you have that, you can think of each piece that you get after prolongations as if you're prolonging ideals of differential equations as graded modules. Then you can put them together. Now that's a module. Then you can construct Kojoule complex of that graded module. This is bigraded. And you can construct HPQ of that complex. Then you can define the notion of regularity for that. That infimum for which HPQs of that complex, bigraded complex vanishes, is the regularity of such modules. So you can actually do it for just vector space. If you pay attention to the notion of symbol in here, it's a subvector space of sim k of something times W. This is analog of here. So there is some sim k of something times W. If you look, these are vector spaces. If you move them locally, you will get local systems like vector bundles. The topological bundles associated to these solution spaces are actually sitting as kind of local systems inside here locally. As algebra, sheaf of algebras, they are quotients of this thing. This has to do with either I'm looking at straight E or curly E. Okay, so this thing surjects onto NK after restriction to ZK. So this is exactly very much compatible to the original abstract algebra, rudimentary formalism. Okay. So now for these symbols, I would like to define some notion of regularity. As I said, there is some notion of regularity that for these symbols you can define. Now, if these symbols are actually, honest to God, come from systems of differential equations, meaning I have replaced my V with this sheaf of Kähler differentials, and I have replaced my W with this bundle E, let's say, then the regularity degree that you define for them using this HPQ cohomology is called degree of involutivity. So an involutive nonlinear PD is the one whose symbol module is regular in the sense I just defined using HPQ. That's right. But if you assume integrability or some kind of a extension of Hilbert's basis theorem, they become regular. Yes, a priori these are infinitely generated, but after some time they might stabilize. So they are almost assumed to be finitely generated. Okay, so maybe this is important. Looking at only involutive, so we want to parameterize involutive PDs. In the language of Quot schemes, we looked at coherent sheaves which satisfy regularity condition of Castelnuovo-Mumford. All of our moduli spaces are constructed over such sheaves. It's not restricted. Literally, every moduli space, useful moduli space in algebraic geometry involving sheaves is made of sheaves satisfying this regularity condition. Same thing in here. We don't want to look at all non-regular or non-involutive PDEs. We want to look at involutive PDEs. But this restriction is not a huge restriction because analytic systems can always be made involutive. And most examples in mathematical physics are of this type, of involutive differential equations. For example, solutions to Yang-Mills equations, Einstein's equations, Einstein-Maxwell equations, higher P-form theories, etc., etc. Okay, so you have the infinite tower of solution spaces, right? And as Mark asked, you want this integrability somewhere appearing somehow. So a priori, the sequence of ideals that these correspond to is not expected to stabilize. But some kind of analog of Hilbert's basis theorem for these ascending chains of ideals can be used. That's actually due to Rit, and it's called Rit-Radenbush theorem, that these ideals actually are stabilized, so I can use them for my purposes. Okay, so here is a definition of one definition of regularity. And as the infinity ideal associated to a Z infinite prolongation solution space is called Spencer regular if the elements in this tower, did I have the tower? These ZRs. So I have a tower of Z's. These satisfy that, first of all, these could be possibly singular schemes, but prolongation of ZR surjects onto ZR. Okay? Think about that prolongation map. You will see that this is actually non-trivial. That prolongation of ZR should surject onto ZR because of what I just told you. You have these involutions backwards and you might not get projected. And the other thing is you want to say that ZL plus R is exactly prolongation of order L of ZR. So this is basically what I just told you. Inclusions become identities. You can go up and down, up and down. So, okay, pictorially speaking, if you have a tower of solution spaces, that means after some degree, these things become nice. This is what Mark was asking. And this is exactly this finite generatedness of these ideals. This gives you this reason for this regularity, actually. Otherwise, these are infinitely generated. Yeah. Okay, so this is what you will get. In analytic category, actually, it can be proved that there is always such R0. And this is due to a theorem of Cartan and Kurnishi. Okay, all right. So, involutivity and the degree of involution correspond to a certain cohomological vanishing condition. Let's pay attention to this previous slide. I gave you a notion of regularity. For modules, I gave you a notion of regularity. For sheaves, it was vanishing of higher cohomologies. Then I said you can do bigraded complex and define this for vanishing of HPQ of that bigraded complex. All of it is vanishing cohomologies. Here, the regularity of Spencer actually is kind of scheme theoretic, is by looking at the tower of solution spaces. So we want to find what is the sheaf theoretic version of this regularity so that we can just forget about looking at the schemes, because I don't want to look at the schemes because there are so many ways of getting to them. I don't want to look at them. I just want to look at some sheaf cohomology, some vanishing, and say this, if this is regular or not. So, okay, this needs the notion of Spencer cohomology and especially delta Spencer cohomology. It uses this language of symbols. So this is, yeah. Involution. This is involutivity. This is regularity. It's not involution. Involutivity. Did I say involution? Oh, I said, then it's a mistake. Involution. Where did I say? Ah, involutivity. It's not involution. Yeah, you're right. That's a bad notation. This is the symbol for E that I put in here. Let's say we assume that we know how to construct this. All right. So this knows everything in terms of differential structure of the bundle E. Once I restrict it to the solution space, tensor it with the structure sheaf of the solution space, it knows everything about not just differential structure of E, but also the solution space. So that gives me the symbol of the solution space. Okay? So this is what we get after restriction. We get this symbol. All right. Now, I want to construct this complex, which gives me the HPQ. I can take my E and define something called Kth-Jet-Spencer complex of E by taking derivatives of the global sections of E. So this goes like this: jet k, then omega 1 jet k minus 1, omega 2 jet k minus 2. It stops at omega n because I have dimension of x is n. So it can start from jet k and go like that. It can start from jet k minus 1 and go like that. And then between jet k minus 1 and jet k, if I look at the kernels, I have these symbols. So kernel of this is 0, co-kernel is 0. Kernel of this thing is kth symbol of E. Kernel of this thing is k minus 1 symbol of E tensor with omega. Kernel of this thing is k minus 2 tensor with omega, so on and so forth. Okay, so the upper row can be completed by this row. This is called delta Spencer complex. It has a fancy name, but it has a very easy definition. Okay? Now, if I restrict this to the solution spaces, I will get the notion of delta Spencer complex for the solution spaces, for these symbols of the solution space. So all I need to do, I look at this, and I restrict to the zk's. And I get some solution, some complex for nk, nk minus 1, nk minus 2, so on and so forth. And those are the graded pieces. And then I put them together, I calculate HPQ. I can do this even, okay, so I'm not going to tell you what it looks like in coordinates. I just put this for PDE people. No. Yeah, here. I can also look at these more extended version of operators from jet k of, after prolongations, jet k plus L of E to jet L of F. Okay, do the same thing. In each level, you can have operations between these. So you have some tower for jet k of E, k plus L, k minus L. You have some tower here, right? Okay. Kernels are given by these symbols of E, symbol of F. There are maps, and I look at the kernel. And the kernels are my symbol. So I get a sequence of, vertical sequence of kernels like that. I can calculate the delta Spencer complex. I can put them together, compute this graded module, calculate HPQ. And that's a notion of regularity. All right? So the regularity for an infinite prolongation of symbols associated to some d infinity ideal of solution space to an infinite system of differential equations is given by this infimum over Q0, for which HPQ vanishes. Okay? If I is formally integrable and in Spencer regular, then it can be actually shown that degree of involution agrees with the Spencer regularity. Spencer regularity is a scheme theoretic. Degree of involution I defined with respect to the system of symbols is sheaf theoretic. Okay? Once I don't want to go here because this is about the proof and so on. once you know that these ideals stabilize, when you're assuming this integrability for them, you actually see that these HPQs after some time vanish, right? So there are finitely many HPQs. So this is useful because it actually allows you to define a notion of Hilbert polynomial for this D-infinity structure sheaf. Remember, we were looking at Hilbert scheme of subvarieties. These were OX surject onto OY, where the Hilbert polynomial Y is P. Now I have O of Z infinity, and I have a notion of Hilbert polynomial for it, which comes from this regularity, involutivity. So it is given by this. You can also define Euler characteristic for these things, right? And you can define, okay, so this suggests development of D-geometric index theory for people in relativity theory here and differential equations. It's very hard to deal with algebraic formalism for hyperbolic operators, but it's not impossible, we think. We haven't done it. All right, so anything that you could do using this construction of, how many minutes? 4 minutes. Anything you could do in regular algebraic geometry, you can do for D geometry. Only the last row is now added to the previous table. So now you have Castelnuovo-Mumford regularity. Here you have degree of involutivity, which is using some cohomology vanishing conditions for the symbolic systems. This allows you to construct Hilbert schemes because here you have a notion of Hilbert polynomial. Here you have a notion of D-Hilbert polynomial. Okay, so D. Of moduli scheme of, I will show you. Let me tell you, moduli schemes of these ideal sheaves, D ideal sheaves, or D structure sheaves, D structure sheaves. So let me show you. So this is the Quot functor. It parameterizes sequences like this up to isomorphism. Instead of fixing the Hilbert polynomial, I fix the involutivity degree because it understands everything. And so we can prove that this defines a moduli functor. So this is our theorem. If X is D affine algebraic variety of dimension n, some m number of dependent variables, some fixed polynomial, there is some Quot functor, which is defined exactly like Grothendieck's Quot functor. It parameterizes the structure sheaf of infinite prolongation Z infinities with D Hilbert polynomials equal to P. Not only that, this is an honest Hilbert polynomial, something like Hilbert polynomial. So you can use it to define reduced Hilbert polynomial, the slope. So you can define some new notion of stability or semi-stability and cut some loci of a stable or semi-stable loci inside the Quot functor. All right, so I'm not going to talk about this. This is about this boundedness, Grothendieck's boundedness. The family is bounded. That means that there is an upper bound, uniform bound for the regularity for finitely many choices of D Hilbert polynomials fixed. Then we have even some notion of Lefschetz hyperplane theorem. If you have higher cohomology vanishing conditions after restriction to some hyperplane section of cotangent bundle, you also have it. You can prove that. I'm going to go fast. You can study deformation obstruction theory over D algebras. It's very similar to Hilbert scheme tangent and higher obstruction spaces. And this is what Alexei was asking. Since you have this D Hilbert polynomial, you can define a notion of semi-stability and stability using lexicographic comparison of Hilbert polynomials. So you can cut semi-stable or stable loci. You can do GIT quotients by stabilizers and get honest to God moduli spaces of the structure sheaf of solution spaces to a differential equation after infinite prolongations. Okay, so you can do many things. You can, in the second paper, we showed how this can have a derived enhancement. Well, we have not done any normative geometry, but that's next. We want to count stuff. Like, for example, I think solutions to Yang-Mills equations or Picard-Fuchs differential equations would give you Gromov-Witten invariance. Yang-Mills equations give you DT invariance, or things like holomorphic Chern-Simons theory on three poles, which gives you Danson-Thomas theory of three poles. These are nice, but these we know. We know like for 30 years now. But can we count solutions to Einstein's equations? If you can develop this theory for hyperbolic operators and for Monge-Ampère type equations, then you can actually define moduli space of solutions to Einstein's equation. But maybe you can do a normative geometry in the context of general relativity. So that's actually what we are aiming to hopefully do, or we dream to do. Thank you very much for your attention.
Thank you very much for this very exciting talk. It was very well explained. Are there any questions? Yes.
At one point, you used the term de-affine.
Yeah.
So the Hilbert schemes, these Hilbert schemes, are they proper over something, or what are they? If you want to get invariance out of them, you have the. I mean,
Yeah.
you have this derived structure. You get virtual fundamental classes. But if you want to get
a priori
numbers,
they are non-proper. A priori they are non-proper. But the ideal, because ideals are infinitely generated operated a priori, and the algebras are infinitely generated. But then you have a stabilization. So basically, these are kind of finite type. Yeah. So in terms of the space, the scheme itself. Yeah. So it's just affine. Yes. I don't know if they are actually can be made proper. Now, in that sense, I don't know. Finite type. They are finite type. Yeah, but they're not proper. Yes.
Yes.
Ask a naive question. What I remember, if I remember correctly, what Vinogradov said about 45 years ago, there was some symplectic structure in this infinite jet space, which governs somehow this this pullbacks, how we call them, liftings, infinite liftings. So this involutivity which you speak about, is it about this? Is it about
involutivity is not about this, actually. It's about involutivity is about kind of finite generation property of the modules over these infinite algebras. But this symplectic structure we think exists, actually. This is how you define shifted symplectic structures on affine spaces. It should exist.
I thought your liftings are kind of Lagrangian submanifolds in this infinite dimension.
Yeah, so good. Okay.
So maybe I misunderstand, but the terminology for involution that I think you might be referring to is in terms of an integrable distribution, right? So this total derivatives, this is this Cartan distribution. So it determines a flat connection on this infinite jet bundle. And this is what Vinogradov looked at, the pairs of these submanifolds of infinitely prolonged equations with this Cartan distribution. And he said that that pair is morally the space of solutions because the integral submanifolds of this Cartan distribution are precisely the graphs of jet prolongations of sections of your bundle. So these are exactly the leaves, sort of, you're foliating this infinite jet space, morally speaking, because you don't have Frobenius in this infinite dimensional setting, but it's morally like foliated by these integral manifolds, which are the solutions basically to this PDE. So this is this D geometric perspective. Instead of trying to formulate categorically operations between pairs of some infinite dimensional space plus a distribution, where all morphisms and categorical constructions preserve the distribution, we look at it from a perspective of just these structure sheets over the ring of differential operators, which is for us acting by lifting through this distribution. So it's more convenient for categorical constructions, but essentially it's containing the same information as Vinogradov's defieties.
But one answer to his question is that we haven't shown these kind of symplectic structures.
So there's this, the presymplectic, this Zuckerman presymplectic form on the jet spaces.
Yes, we have not shown it. The answer is we have not shown it, but we will show it. But I cannot give you a proper answer.
Yes.
Should exist, I think.
There's another question.
Hi, I want to ask about is there a possibility to do this story over not variety but stacks? The reason I ask this because there are classical story of Cardan on the G structures. So, for example, symplectic structure or complex structure as the G structure for which G equal to symplectic group.
If I use proper cohomology theory over the stack, I think it can be done.
Yeah,
But
so
that has to do with the right choice of cohomology theory.
yeah, so for example, if we want to
Maybe
incorporate
I need tameness.
tameness.
Yeah.
Okay, if we try to incorporate the derived symplectic structure, derived stack along the line of the Cartan's idea of G structure, and using this machinery, so we need to describe the jet bundles on a derived stack.
Yeah.
And
that I think can be done. Jet bundles and derived stacks can be done. But construction of this geometric underlying space actually over stacks comes before that, right? If you want to go derived, you can construct everything derived. So if you want X to be a stack, you need this tameness kind of property so that you can have some well-defined notion of cohomology. But after that extension to derived stack, I think it's just automatic. I don't know. I shouldn't. Maybe
okay.
To my eye, yeah. Have a look at our second paper.
Okay. How about the vanishing of the Spencer cohomology? So you said that the regularity is basically saying that the obstruction class in the Spencer cohomology vanishes. Right?
That's right.
Yeah, you said there are
once we have regularity over the original stack, then the derived enhancement is actually automatic.
Okay.
That we have shown. That's actually a very detailed proof. But that can be.
Okay. Thank you.
Well, anyways, never mind.
I see there's another question.
I wanted to say something. Yeah. Nothing. Yes.
I'm not sure if this question is related, but I'm wondering if we can just take some results in classical Riemann-Hilbert correspondence in a linear case to here, because as we can define the characteristic variety as similarly, I'm wondering but we cannot define holonomic because it's infinite dimensional. So is there some kind of analog, or what can we say about this?
I think there is, right? I mean, we have this analog of characteristic varieties. Yes.
So yeah, we let our submanifolds ZK be arbitrary fibered submanifolds. If you impose that they are, if you look at JK as a vector bundle and you ask that they be vector subbundles, this linearity structure imposes that they're linear PDEs. And now if you ask that this prolongation tower actually becomes all isomorphic at some point, which actually is called finite type PDEs, this is what is also called holonomic in the D module literature. So it actually means that not only Spencer cohomology stabilizes, but actually the symbols, these NK, are 0 for high enough K. So they just disappear.
Are there any more questions? Okay, so let's thank the speaker again. This was a very exciting talk, in fact.